Hi, my name is Justin Mimbs. I'd like to introduce you to a fluid model that we implemented at IC Tech, which is capable of modeling water waves as they approach and wash over the shore. Over the next few minutes, we'll walk through some of the benchmark tests used for validating a numerical tsunami model. These benchmark tests will serve as examples to show what the model is capable of, as well as the Julia code for using it. But first, let's look at an example. Here we see a rectangular portion of a coastline with a small island offshore. The seabed slopes gently and the land rises steeply at the shoreline. The water surface is initially flat, which you see as a gray sheet. A tsunami is generated from the left side of our wave tank, leading with a depression, which you see in red, causing the shoreline to recede. The surge follows, reflecting off the shore and the walls of our tank, and even overtops the small island. Our implementation is based on the model formulated in this paper by Yamazaki and others. We implemented it in Julia because we needed to simulate coastal inundation as part of our research. We wanted to use Julia, but we didn't find a package at the time that fit our needs. Julia's ecosystem for numerical computing made it feasible for us to write our own. As I record this, the work is not a published package, but we do plan to open source the package by the time you see this talk at JuliaCon. So if you're interested, I'll make sure there's a link to the repository on the YouTube page. The authors of the model already showed validation results in their paper, but we as software developers still need a way to verify our Julia code as we write it. A list of criteria for evaluating a tsunami model is published here on the NOAA website. These criteria include checking basic hydrodynamic considerations, like solution convergence and mass conservation, as well as comparing simulation results to various benchmarks. For some scenarios, wave theory gives us analytical solutions that we can compare to. And for more complex wave interactions, laboratory experiments conducted with physical wave tanks give us measurement data to compare to. For the rest of this talk, we'll look at these 4 benchmarks as examples. Okay, the first benchmark we'll look at is solitary wave propagation. A solitary wave is a wave that moves without changing shape. This problem has an analytical solution given by the equations on the right. Water waves like this do occur in nature, so we want our model to be able to reproduce them. The shape of the wave on the surface of the water looks like the red curve you see here, and as the wave moves forward in time, it maintains its shape. This is the figure we're going to try to recreate with our model. We define a solitary wave in Julia using the same definitions as on the right. We can initialize our model using that definition of a wave and a parameter to scale the grid resolution. We define our grid by its x and y domain bounds and by its resolution. We define the basin. Here we're passing in a number to define a flat basin at that water depth, but we could also pass in a function to express more complex bathymetry. And we initialize surface elevation and particle velocity using the functions from our wave definition. And that is enough to create a model and see what it looks like. Next, we'll run our simulation. We do that by providing the model that we want to step forward in time, as well as a file path to save the output to. Let's run it with a grid scaling of 50 grid cells per wavelength. Our domain is 5 wavelengths long in the x dimension. Now that it's finished running, we can plot the first result. And when we iterate through the results and update the figure, we see an animation of our wave. And it does look like it's moving without changing shape. Let's compare the model's results to the analytical solution from above. The shape stays similar, but we can see that the wave is losing some height over time. This is because of the rather coarse grid resolution we used. I ran a simulation earlier with a finer resolution of 200 grid cells per wavelength, and we see in those results the height of the wave is much more stable. This is the property of convergence we're looking for. As we increase the resolution of our model, we want the results to converge toward the same, hopefully more accurate solution. Finally, let's look at mass conservation. We do that by comparing the volume of fluid we have at each time step to the initial volume of fluid our model had. Here, after more than 500 time steps, the volume of fluid has hardly changed at all. Now we'll look at some laboratory benchmarks. I've already run these simulations, so we'll just take a look at the results. The first benchmark we'll look at is solitary wave on a simple beach. This is based on an experiment by Sinolakis done in 1987, where he sent solitary waves at a simple plain beach and captured the shapes of the waves as they ran up the slope and drew back down into the water. We compare our simulated results with the lab data. Here we're looking at the profile of the water at 4 points in time. And we see that our model recreates the transforming shape of the wave quite well. When we look at mass conservation for this simulation, it's not quite as stable as the previous example, and that's because the fluid is running up and drawing down on a beach. NOAA gives the guidelines that the volume of fluid shouldn't change more than 5% after run up and draw down. So at 0.2% here, we're well within that guidance. The next benchmark is solitary wave on a conical island. This is based on an experiment by Briggs and others in 1995, where they set up a concrete island in the middle of a large wave pool and sent a solitary wave at it. This is our simulation of the experiment. You'll notice that the wave exits the domain here, and that's because we're using open boundary conditions to let the waves pass through rather than reflect back into our domain. In the laboratory experiment, they used wave gauges to measure the changing surface elevation at various locations in the pool. And we'll compare our results to the measurements at those wave gauges, and we see the model does a good job simulating the motion of the water. They also measured the maximum height that the water reached on the conical island, and that's the comparison we see plotted here. Again, our model is in good agreement with the lab data. The last benchmark we'll look at is tsunami run-up on a complex beach. This is based on an experiment done by Matsuyama and Tanaka in 2001. They set out to recreate the conditions of a real tsunami that occurred in Japan in 1993. They constructed a scale model of the region in plywood, and they generated a wave in the pool based on observations from the real event. At the bottom of this figure is the surface elevation of the laboratory wave as it entered the domain from the left. So we use that surface elevation data to generate the wave in our simulation. This is the same simulation we saw at the beginning, but we'll watch it again. When we compare our results at the 3 wave gauges, we see pretty good agreement in all of them. The phases shifted in a few places, but the shapes are captured well. Overall, it looks good for such a complex case. Thanks for your time.